Designing a vessel implies considering all the loads at the proper location. We are talking masses for the earthquake and foundation loads, surface exposed to wind, as well as loads on nozzles or flanges. We'll be exploring them all in this load types chapter. We'll be using this vertical vessel on skirt with a nozzle at the top and a body flange as an example for our explanations. Now, let's go. The first loads we come across appear at the model creation. We refer to the load conditions. Coming back to our model, we double-click on the background to go to the vessel properties, then go to the load conditions tab. Here, the first thing we see are the load cases: lifted, erected, operating, and shutdown. In the operating case, we see that in the accessories group, almost all elements are checked, both in the weight and the load side. Weight refers to the consideration of the mass in that case, while the load refers to the surface exposed to the wind. See that, for example, in the lifted case, nothing is checked. This means that our piping is not yet connected to the nozzles, the platforms and the ladders are not installed, fireproofing is not in place, and so on. Please check whether these default values correspond to the actual conditions of your vessel. Because this will affect the foundation's loads and, of course, the structural check of the thickness. Down below, you can input the different loads. We have the wind. When you click, you can see the list of all the design codes available in the software. Dialog changes depending on the code that you choose, just adapting to the different parameters of that code. I'm going to check EN again, and here I'm going to insert my dynamic pressure. Since I do not know it, I'm going to click on the question mark here, and I'm going to use the calculator embedded in the program. I'm going to go for 120 kilometers per hour. I just convert, and I see that it's 68. So I close here, and I just type 68. Then I say, okay, the rest of values are good for this example. Then be doing the same for the earthquake. Here I will be choosing EN. The soil class is going to be A, and I will be using shape spectra type 2, normalized spectra for this, and then ES. You can see that my load combinations have changed, now included both my wind and my earthquakes for the different load cases. And this is the fair load types that we have. As for the second type, we are referring to the external loads element. This is a multifunctional type that will allow you to model any type of loads on a geometry element that cannot be modeled otherwise, or to consider the impact of elements that cannot be modeled in the vessel. To include them, you go to the menu Insert, Load. Here we'll be going for a tag designation that will allow you to identify it better. Location along the equivalent beam, so for example 5 meters, and here you have the different load cases from before in which that load will be applied, and we have vertical, horizontal, and bending moments. In a vertical load, of course, by default is going to be go downwards, so it's a weight, and a horizontal load, for example, of 300. Then we say OK. Here you can see the signs per default and the location on which it's going to be applied, so at the center of my equivalent beam. Another type will be the loads applied on the nozzle by the piping. This time in the model, we'll be clicking on the nozzle element, whether in the sketcher or in the list of components. And as long as the nozzle type is set as process, meaning there's a piping connected to it, you will be having the local loads tab available at the top. We click here, and you can see all the different types of loads that you can input. You can have these loads filled from a customizable file. That's how the fill from standard button works. He's going to read a customizable file with an Excel sheet where the different expected loads, depending on the nozzle diameter and the flange reading, are listed. If not, you can always reset and type it by hand, respecting the sign as shown in the images. Then we click OK. These loads will be used for the local load checking of the opening, but will not appear in the foundation loads unless you create an external load. As we saw before, nozzles are not geometry elements and thus not transmit forces to one. The last type of loads are loads directly applied on the flanges, resulting in increase in rating. In our example, we have two types of flange. We have a standard flange attached to our nozzle and a body flange. We are going to double click on the nozzle element, then in the nozzle properties dialog, click on the edit flange, and here at the bottom, just beside the rating, we have evaluation of external loads. We check this case, then we go to the external loads to define them. Gasket circle, I'm going to go for 202 millimeters, and then operational load, a moment. Here I can specify a different moment factor than those of the table from the norm. I just click OK. As for the body flange, I double click on the body flange, and this time go to the gasket tab, and here at the bottom I have evaluation of external loads. Click here just as before, and I have the external loads. I'm going to input one load and one moment and just press OK. Now that we have input our loads, where are them in the report and how to read them? First of all, let's run calculation. We can click on the calculator on the toolbar, or in the menu go execute, calculate strength. We save changes and we let it calculate. Now that calculation has finished, I can see my results in the bottom left corner. First of all, we'll be looking for the load conditions. We are going to follow the same order. So in a vertical vessel, these three reports refer to those load conditions. We'll be starting with the definitions. So we click in the then show selected report calculation detail, and we see how it opens in Word. First, we land on the explanation of a table that will be seen in the next report. This refers to the different stresses and minimal thickness, considering the internal or external pressure and the external loads. Then we have explanation of a second table that we will see in the following report, not in this one. Well, we will be checking the different thickness. If you see closely, we are doing the difference between the external and internal diameter, which is the thickness. Then we can see the wind loads definition. This is for the lifted case. By default, the wind defined in my operating case will propagate to the rest of cases. Here you can see the values that I input, as well as all the intermediate equations to obtain a wind profile that will be applied to my equivalent beam, depending on the surface exposed to the wind and the shape factors. You can use your navigation pane at the left to see all the different cases. Earthquake condition, this is an operating case. You can see that by default, my earthquake case does not apply in the lifted condition, but you can, of course, set it otherwise. Here you can see the earthquake definition, again with those all the initial values, intermediate values, and even a nice graph with my normalized spectrum. We'll be closing here. Then we'll be seeing the different cases. As you see, for example, we'll be starting with wind. We click on the proper case, then show selected report calculation. You can see here at the beginning the summary of the different projected areas and weights. Also, the summary of the external loads that I input. If you remember that external load applied at 5 meters. Here you have a calculation of the period and the center of gravity for that case, taking into account that in that cases we are considering some weights dependent on the weights of the element for which we check the box in the dialog. Then here it's a calculation of the different forces that will be applied. In our equivalent beam is subdivided in smaller parts, and in each part we'll be assigning a shake factor. We'll be calculating a difference force based on the height and also on the surface exposed to the wind by that element. See different forces here. Here you can see first the foundation loads for that case, then nice graphs representing the bending moments, stresses, and deflections, and just below the maximum values for each graph. Then we have this table referring to the different stresses and minimal thickness. The explanation for this table, we saw it in the definitions report from before. And just next, we have the second table with the different stress calculations for which the explanation was in the previous report. There are so many rows because our equivalent beam has been subdivided in a smaller element to ensure accuracy. I close this one and I will move in to the next one. Then we have detailed characteristics of the equivalent beam model, my favorite one, where the loads are really going to be applied. Here is a summary of the different thickness and values that we'll be using, then some loads for determining the period, what that we saw before. And here are the details of the different horizontal loads that have been applying and where they come from. Here you can see all winds, but also my external load applied at 6 meters from the ground, considering that the skirt measures 1 meter. All wind forces well calculated as described in the 2 previous reports. And here we can see the summary for the vertical loads. Which is really interesting about this table is that you can see some what I call ghost elements. Here you have the piping. We are assuming that this process type nozzle is attached to a piping and we are considering some part of that piping. For more information on that, please go to the help contents, just type piping, and you'll be seeing that AutoPipe vessel considers that some part of that piping attached to it is impacting our nozzle and our shell, and that is being considered to ensure safety. Also, we have some ladder loads. This is because we check the ladder for operating case, and even though we haven't modeled it, although we could have, he's supposing that we will be having one just to be sure that we are being conservative enough. We will be seeing the same for the different earthquake. I'm going directly to the horizontals, and here you can see my different earthquake loads applied at every subpart of my equivalent beam. We already saw the load conditions and the external loads, how they can be found. As for the local loads applying on the nozzle, we're going to the isolated opening report, the report of my nozzle, then I say show selected. And in my navigation pane, I go to local loads on nozzle, and you can see here that my loads have been upchecked using the local loads method chosen. You can see here the loads I applied in the dialog. As for the loads on the flange, we can see the loads applied on the nozzle in the summary of forged items. We click on show selected report calculation. And you can see evaluation of external loads just below the checking of the different standard flanges. You can see my equation, the different values that we input, and if you hadn't checked, we will have a message in red. Then there's just one load missing, the loads applied on the body flanges. I go to the body flange report and then show selected report. Here you can see in the first page the loads that we impose appearing in blue and that they will be considered all over my calculation, as you see here. Now you should know everything you needed to know on loads, how AutoPay Vessel considers them, how to input them, and last but not least, where to find them in the report and how to read them. Thanks very much for watching.